So my name is David Brown. I'm with Lenaro. I've been working on Zephyr for, oh goodness, it's like 7 years, something like that. And about 6 months ago, something like that, 6, 7 months ago, I started working on a project to bring Rust support to Zephyr. And not just, oh, look, cute hobby project on the side, maybe we can sort of make Rust work, but actually have it part of the project. So I guess the first question is, why would you do Rust on Zephyr? I know Rust is getting a lot of hype. Zephyr's getting a lot of hype. They're not necessarily the same kind of hype. Um, but the benefits that Rust brings to this picture is a language built around a lot of these safety ideas of especially memory safety. If you go look at vulnerability reports, there's use after free buffer array bound issues are kind of the most common things that cause vulnerabilities. And the Rust language gives you protection against those things as part of they're compile errors. They're not things you have to detect at runtime. Rust also brings us some kind of more modern tooling. At least from the Rust side, there's a crate ecosystem of an extremely large number of what are called crates, the unit of compilation of Rust code, and this cargo tool for building all of this, specifying dependencies, assembling the whole thing. Um, a couple things. This idea of memory safety without a garbage collector. There's a lot of memory safe languages out there, but it's traditionally done by using a garbage collector, which isn't that great of a combination with a nice embedded real-time system. And Rust really has kind of embraced that. The thing that came out of doing that was this thing that's been termed fearless concurrency. The idea that these mechanisms that were added to the language to help you with memory safety, they also really easily help you with concurrency safety. That there's these attributes that are added to types that indicate, is this safe to share across threads? Is this safe to send to another thread? They're actually called send and sync. And these help with that kind of development. So what was the goal of this project? So first of all, it was about writing applications in Rust. If you've seen some of the stuff going on with the Linux kernel, this is not like that at all. There may be future efforts to add code to Zephyr, but that has its own political battles and fights and things that will need to happen. And the goal here was, as a developer of an application running on Zephyr, can I write it in Rust? And can I write it entirely in Rust? And even more ideally, can I write it in Rust without having to sprinkle unsafe keywords all over my code? So part of that is these kind of clean bindings to the Zephyr API. There's a bit semantic differences between how Rust likes to do things and how typical kind of C bindings like to do things. And can we make kind of nice clean bindings? That's kind of a little misleading when it says device drivers, because we're not writing device drivers in Rust. We're interfacing to Zephyr's device drivers, but trying to do that in such a way that it's compatible with the async kind of concepts that you find in typical Rust code. And there's divided into two parts. The second talk is going to get into async a whole lot more. And then I wanted it to be a very simple developer experience, that this wasn't some, to cite an example of one previous Rust on Zephyr project, the steps started by cloning the entire Rust compiler toolchain, making modifications and building it yourself. So part of the goal here is this needs to build with stable Rust, where at that point I do have a minimum Rust version of 1.85 that I can go into if you have concerns about why I did that. It's basically so that I can support the new 2024 edition of Rust. So not goals. We're not rewriting Zephyr in Rust. That's a different project. So, we're not replacing Zephyr's build system. And we're not replacing Cargo, Rust's build system. I mean, both of those are kind of important. If you look at the way the Linux kernel does it, they're not using Cargo. They've incorporated compilation of Rust code as part of the Linux build system. And if we do rewrite parts of Zephyr in Rust, something similar will probably happen. But as an application developer, it's really nice to be able to just say, oh, look, there's a crate that does this, add that to my cargo.toml file, and cargo develops and built that. Now, the way that works, Zephyr's build system is based on CMake and Python and some other things going on there. And it builds the whole system, and then we have one rule that says, oh, there's this .a file for this thing written in Rust. And to build that, first of all, you always do this. We don't try to have CMake figure out the dependencies. Just go run cargo build with these arguments. And I actually put a lot of work into making a .cargo/config.toml. It's an awful file name to remember, that you can symlink into your project, and suddenly Rust Analyzer works, your IDE works. You can do things like cargo format, cargo blah, blah, blah. Many of those just work. Anything that doesn't expect an executable should just work. So here's what you do when you build something. So Zephyr uses West, which has this kind of module system. There's a Zephyr tree, which has got a CMake lists file in it, kconfigs, boards, drivers, lots and lots of other directories and files in there. And then there's this modules directory that sits next to that directory. And inside that are things like HALs, anything that doesn't live in this main repository. And the new thing that's in there is this module called Zephyr Lang Rust. When we first started out, we had a bunch of discussions. Does this live in a module, or does this live in the main Zephyr tree? We ended up deciding to put it in a module. I believe that was very much the correct thing to do. There's a lot of differences in terms of what CI wants to do and that kind of thing that makes it kind of unpleasant to be working on one little piece that lives in the main repo. And then you would typically have something like my application, and you'll create a CMake lists like you would. This mostly looks like a Zephyr. There we are. Well, that's not very bright. This looks like a Zephyr. You know, if you go, how do I build a Zephyr app? Well, you create the CMake list, you create a project. But then we also create a cargo.toml and a source lib. Yes, it's a library. If somebody really wants to figure out how to convince cargo to call that main, we can, but it really wants it called lib.rs. You then build in my app, you do West build, and this just builds your application. So where are we at right now? So you can build Rust applications in Zephyr. I've built them. I have a hobby project, which is a keyboard, which I run code written in Rust, and it can run on Zephyr. It's integrated with cargo, and the CMake builds Zephyr, calls cargo, builds the Rust code, and then there's a whole bunch of bindings in the Rust code. So we have all the synchronization things: timers, atomics, channels, mutexes, condition variables, arcs, semaphores. That almost sounds like a song. There's threads, and these are declarative. I don't think I have an example in here just because of the short time frame, but I borrowed this from the Embassy project. As far as you have a function at the top level, you put an attribute in front of it that says it's hash bracket Zephyr : thread open paren. You have to give the stack sizes the mandatory, and there's a few other things you can put in there. And then suddenly you have this thing that looks like a function from the rest of the code, but when you call it, it returns a thread handle and not it doesn't just do the work of the function. And then that has one method on it called start, which will then start that thread. And then the thing you get back from that has a join method and some things like that. But it really simplifies the way that you declare these things. You've got work queues. These are Zephyr mechanisms. Logging, which we can get into if you have more details. There's a fairly significant semantic mismatch between C's idea of printing things and Rust's idea of printing things. And so the kind of naive, simplistic way of going forward with this, you end up with a lot of code in there to kind of translate back and forth between these. It works, but it's probably not where you wouldn't really want to build a system like that unless you have lots of code space around. A device tree. So the device tree is kind of a big thing for Zephyr, as Kate mentioned. It's a hierarchical tree that describes what devices you have. I actually read the generated device tree for a given build and generate a tree of Rust modules that mirrors what that is. And we'll see that in a minute with an example that you actually just name the path to your node directly in the Rust code. And there will be a function in there called getInstance, which will return the nice Rust-friendly handle to that given device. And as far as kconfig goes, so kconfig, taken directly from Linux, is configuration options, but these are visible in Rust code for things that have values like numbers and strings. They're just constants in a module that you have access to. And then there's another mechanism to allow Boolean kconfig options as well as node presence in the device tree to be CFG flags in Rust so that you can do conditional compilation based on how your Zephyr build was configured and what devices might be present. And then I have basic async support in here. This is essentially, we'll get into this with the next talk in like 10-15 minutes. But you have the ability to run these asynchronous threads, or tasks, I think they're typically called in Rust, which are it's a cooperative type scheduling that can then be run. You collect a bunch of those and you can run them on a single Zephyr thread. And it gives you kind of the advantages of both. You get the low overhead of scheduling without context switches, and then you have context switches when you need them, and see the next presentation. There's also a timer driver. It's like a dozen lines of code that implements the timer that a third-party library out there called Embassy wants, that then makes a whole bunch of the Embassy code all just works fine. This code is just perfectly usable on top of Zephyr now. And it only took writing, it's less than 100 lines of code to make all of that work. There's more that's coming. Right now they don't get along very well, you might say, that like the async Rust threads can't wait for a Zephyr semaphore. So that's something that needs to be done. But it's surprising how useful this already is. So here's an example. This is real Rust code. I at least compiled this before I pasted it into the slide. So the first thing up here, no standard. So we don't use the standard library. Feel free to ask me why later. I won't completely go into it, but we're not a desktop OS that is typically what's assumed with standard. A couple of years ago, the Rust project actually split standard into core and alloc, so that for this very reason, because you typically will have a lot of these things that are, not file systems and network stacks and stuff, but that are core things you do need in your language. And so that's been put in the core library, which we have, and this tells it we don't have the standard library. So use is how you bring things into your namespace in Rust. So I'm bringing in Zephyr raw GPIO output active. That's directly from a pound define in a Zephyr header file. And then this Zephyr crate is mostly how you talk to Zephyr. There's a module in there called time, which has sleep and duration. We then have main. Right now this is manually done. I'm probably going to make a macro so that this looks like just a simple decoration. You can just say, oh, Rust main, or Zephyr main probably, and then write a regular. But what this tells it is no mangle, says don't use a complicated string assembling the module path and everything, making it unique. Really call the function Rust main. Oh, and it should be callable from C code. So the first thing we do here is we go to Zephyr device tree aliases LED0 get instance unwrap. The first thing you notice is this is inside of an unsafe. We can have a long story about why, but basically the idea of a GPIO in Zephyr is not safe as far as Rust is concerned, and at some point, you just have to tell it that. And so we get this GPIO pin back, this thing here. Now, if I'm in my ID, I can hover over this and it actually tells me the type. This is GPIO pin, and I can go read the documentation on it. But this thing has a method called configure, and this GPIO token is gone. So apparently I lied when I said this code worked. Okay, there was a change in the API. There used to be this global token that you had to pass around to ensure safety. I kind of convinced myself and some of the other people that that's a little too onerous, that the way Zephyr defines GPIO pins, it's not defined whether it's safe for multiple threads to access different GPIOs, and we'll just kind of leave it at that. It turns out it is actually safe on most platforms. So, but basically say this was an output pin. We create this thing called a duration, and then inside of a loop, we toggle the pin, which doesn't need a token now, and then we sleep. And then this makes the nice light blink. And you can build this, you can run it on your board. I don't have a board here, but it does really work. So what actually works at this point? So the core Zephyr APIs are accessible, what I talked about before. Async executors can run in threads, and there's small, real apps that are running on real hardware. And there's a lot of community interest growing. I think I've received 3 pull requests this week while I'm here in this, so that's always a good sign. 2 of them were people that had started working on something that I've already done, but the people doing pull requests, by the way, if you're going to do pull requests, look at the other pull requests that are open and make sure you don't redo one of those that's there. So what's next? You know, where are we going to go from here? With the caveat that in 2 weeks this stops being my full-time job, and well, if somebody pays for it, it can be, but we'll see where it goes. So expanded subsystem coverage. So right now, none of these things have APIs. You can certainly use them from Rust. Rust doesn't have a problem calling C code. We have a thing built with bindgen, so it's not difficult to just call the functions, but they're not very friendly from Rust. You have to wrap them in unsafe, and you have to deal with the mismatch between Rust's memory model and what C wants. So it's about building better interfaces to these things. Part of that is much more driver coverage. You know, this is great if you want to build a device that blinks lights and spits messages out over a UART. But as Bill mentioned, that's not really the first class kind of support you'd want. And I have the starts of an I2C, but there's way more drivers than that in Zephyr. And in fact, drivers are one of the big reasons to use Zephyr. And it'd be nice to have these as clean interfaces. But I do want to also take the time to do it so that they're very clean in Rust. They're not just a clunky thing to try to bridge between C and the Rust world, but really how you might expect a driver to work. And a lot of that comes down to using, there's a project to build these HALs for Rust, for like bare metal embedded. And those define interfaces, they well, traits in the Rust world. And if you implement those, that's kind of a common interface. So that's kind of a goal to strive for that. What you realistically find is there's a lot of things I haven't thought of yet, but you know, we'll get there. Deeper async, what I was mentioning before, it would be nice if the Zephyr semaphores from an async thread, you could say, oh, well, let's do an async wait on that and do an await, and it will really wake my thing up when that semaphore is available. I have some ideas about how to do that. It's just a question of efficiency and that kind of thing. Better DT integration. I've been chatting with Martí Bolivar about how do we want to, as Zephyr improves its device tree story, how to make sure that the Rust integration with that improves with it and goes along with it. And then I mentioned better logging support, that right now the logging is kind of a, if you enable logging, basically it does the equivalent of sprintf from Rust, and then passes that on to a log message on the Zephyr side. So you end up with this kind of extra allocation that's kind of silly. And then the last point I have up here is user space. User space is a big and not big thing in Zephyr. I don't know how to explain it. There's people that it's important and critical to, and a lot of people that don't care. Right now, you can't have Rust code that runs in user space, predominantly because you can't do a critical section in user space code. So this mainly comes down to needing to implement an optional version of the critical section that you just use as a mutex. And you'll get a performance hit when you do that. There's a reason it's not that way normally. So the challenges. Well, maintaining bindings. You have a language mismatch here. Code is written in C. There's a lot of code in Zephyr that's very much written in C. If you understand what I mean by that, it's like, oh, well, it's C. We better use static inline and lots of macros. And there's a lot of that in there. BindGen tries to call your code, but if it's a static inline, it has to write a wrapper so that you can actually call it. And, macros don't sometimes get through, sometimes don't. You might have to kind of wrap them. But if there's changes to the API in the C side of Zephyr, they're going to break the Rust code. Now, we're in CI, they'll get flagged. We have one showing up right now. The other challenge is, mapping C APIs to safe Rust patterns. C doesn't care if you have multiple mutable references to a value. It's usually wrong if you do, but the language doesn't care. And then we have a lot of cases where who owns something is just kind of implied. And so we have to actually make that explicit now if we're going to make a Rust interface to it. And then the other, kind of the biggest challenge that I run into with this is it's a small ecosystem. Getting 2 reviews on everything is sometimes really challenging because that means pinging both of the other people that are willing to review. A lot of the issue that I find here is people don't feel they're qualified to review the code. I find either people they know Rust really well, but they don't know anything about Zephyr, or they know Zephyr really well, but they aren't so sure about the Rust code. And so there's only a couple people that really feel comfortable reviewing the code. So if you want to learn all about this and become a reviewer, that would be really handy. Even better would be to contribute. So how do you get involved? Well, step 1, try it. Go tell me where my documentation is wrong. Suggest improvements, submit patches, help build these APIs, spread the word. We're on Discord. Zephyr has a Discord. There's a #Rust channel there where most of this discussion happens. And then there's the Git repo to it. Go contribute. At that point, that's it for part 1. So I'll do the standard open it for questions, and then once everything settles back down, we'll let people come back in and start part 2. Any questions? No alloc. Yes, alloc. There is a kconfig option. Oh, so the question is, do we have alloc? Yes, we have alloc. There is a kconfig option on the Zephyr side called rust_alloc. If that is enabled, the alloc crate just works. It uses the common allocator that's now what Zephyr uses for the default, but it actually just uses whatever malloc you have configured for Zephyr. Yeah, it does. It actually works fine. My keyboard firmware uses it for the data structures for this complicated dictionary lookup. So it was. I started actually with a lot of these mechanisms. So there's a thing in the standard library in Rust that kind of assumes you have alloc, and memory safety, because we have alloc, is an easy way to solve a lot of problems. And some of these issues with like a statically declared Zephyr semaphore, it turns out that was really hard to do, because in order to statically declare something in Rust, it has to be a constant constructor. And the Zephyr initializer for semaphores wants to put self-referential pointers inside of the semaphore, and you can't move those. And the kind of default semantics in Rust require that it get moved after the constructor before it's stuck in the static. So there's an atomic variable that manages the initialization state. So it actually works pretty well. It's lower overhead than the previous solution that I had. But that lets you can stick your semaphore in an arc, or you can make it static. They both just work, and it works like you just would expect it to. And there's still a handful of things that still depend on alloc, and I'm trying to work out some of those so that it's not a requirement. Anything else? All right, well, thank you. I'm going to give a couple-minute break just to make sure that anybody who wants to come in for the second part will be here for that part.